Okay. All right, folks, welcome back. This next session is the statistical models and ergom, sort of a brief review. Again, we have a much deeper treatments of all of these features on the web videos and the slide decks that have been shared, and also code that goes with each of these. So if you want to look how to do each of these things we're going to talk about next, that's all right there. The thing I probably to start with is the big picture issue is that what we're talking about with statistical models of networks is fundamentally it's an application of random graph theory to substantive questions, and that application has generated a really wide array of topics that people have studied. And so there's this long and rich and really, like, if you're a geeky kind of methods person, then it's really fun to dig in and fill out the history of this. For those of you that are interested in the history, Stan Wasserman wrote a really nice history of statistical methods and networks for our Oxford Handbook of Social Network Analysis that Ryan Light and I edited this last summer. So if you're interested and you want to copy that, hit me up and I'll pirate you a PDF and send it your way. But it's a nice, it really highlights the fact that this field is just really, really deep. And it all starts with this basic idea of an Erdos random graph, which is, you can imagine what that is. That's if you can imagine this adjacency matrix object we've talked about thus far. If you could treat each of those rows and columns, each cell of that matrix, as a binary variable that you flip a coin some number of times, if it's a weighted network, then you'd get a weighted version of it. That's what an Erdos random graph is, right? And so that each cell has an independent probability of being on and off equal to the density of the graph. Well, then what we do is we just constrain that in various ways. And those different kinds of constraints give you every other model. And then you add those constraints are not just constraints on the network itself, but perhaps divisions or partitions. And so you get constraints between parts of the network. And so there are ways of thinking about each of the things we do that goes into the others. Now, at the same time that we've had this revolution or extension of random graph theory, we also had all of these things that came out of modern Bayesian statistics, particularly things that have to do with things like latent space models and the ability to fit these really complex models that have lots of non-independence built into them. And so those models were fundamentally untractable 20 years ago, and they've become tractable. Sometimes they're slow, but they're still tractable. And so thinking about those in interesting ways is part of what we're doing. So the way that we've set up the class, for those of you that had a chance to read the deeper pieces or to watch the videos, is to think about some basic randomization things, some sort of simple bits that have to do with it. And then that's going to be the background and the lead up to the exponential random graph or ergom model. And the ergom model is really a starting off point for lots of deep analysis questions that people are interested in. So I'm going to replicate that same idea here and try to just quickly go through some of the points in which I think that the highlights that you would have gotten overall. The basic problem with the random graph model is that oftentimes what you're really trying to do is to figure out whether or not the network you have fits into some subclass of other networks. The problem is you can never enumerate the denominator for that problem. The subgraph of all networks that have whatever characteristic you're talking about is usually ginormous. And because of that, you can't just you say, well, the probability of seeing my network is X, because you don't never know what the denominator is. And so instead, what you need is some kind of a construction rule. And that construction rule helps you understand the structure of the network. And I'm using this right here is a fun little fact from random graph theory, which is that if you flip that coin on a network and your density is below a certain threshold, then you never get any connectivity. If it's beyond that certain threshold, then the connectivity goes quickly. And that's a notion of what's called an emergent property. And what's fun about this is that the only information in this little graph you see here is this average degree. It's the number of ties each node has on average. But the random simulation for each of those fits this curve perfectly. And so if I wanted to look at what a random graph work with an average degree 2 is, I guarantee you it's going to have a 80% of the nodes in the largest connected component. So really simple things about the structure of the graph, it turns out, are constrained by something as simple as the number of nodes per number of ties per node. Then if you think about what a random graph is, right, this notion that I'm just flipping a coin, I can flip a coin to try to match what I've seen in the real world. And so this is what I mean by those kinds of constraints. And this is a simple version of that. So imagine that I've observed a network where I have three kinds of kids: white kids, black kids, and other race kids. And I ask them how often do they tie with other, do they have relationships with other people in the network? And so I can look at the real world and it'll look something like this, and then I can generate a network at random that matches it. And if you look at those two networks, they have the exact same mixing matrix. That's what this probability thing is, but one clearly looks different than the other. And so what that's telling you is your model isn't complete. There's something in the real world case here that's constraining the network in a way that this simple probability matrix does not. And so you want to figure out what that is. Well, one thing is the degree distributions don't match, right? And so you can fix that, or you can fix other things about reachability and so forth. So there's lots of things you can do to make that happen. And so the entire branch of models that are designed to explain a network are built around essentially variance of an Ayers-Randy graph, and you can think of them as variance with constraints. Now, the other thing we do with statistical models of networks is try to predict an outcome or compare an association between an outcome and a network feature, and ask whether or not that association is significant. And significance tests in network models are a little bit weird because we don't have a population to infer to. So the inference question isn't given a sample of people from a population, some of whom I give medicine to and some of whom I don't. What's the probability of the people who I gave medicine to being healthier than the people I don't? That's the classic inference problem in the real world. And what we want to know is if our sample is big enough, we can generalize to the population as a whole, assuming that it's a random sample. That isn't the inference question for networks, because by assumption, you have the population in your network. So whatever the relevant population you have, you've observed. And so what you've observed in your network is the truth. So this is what the association is in this population of people at this point in time. This is the exact association between self-rated health and centrality, for example. But that rarely convinces reviewers, right? They want to know, like, well, all right, so what we really mean is it big? And so what we're asking is it big relative to what you would expect by chance? So given the network that I've observed and the association I've observed between my network statistic and my outcome, is the association I've observed in this case bigger than I would expect from a similar random network, or a network in which I've broken the association between the two and just randomized it? And so those two slightly different questions lead to two slightly different ways of answering the question. But in general, what you're going to do is compare a random version of your network, either a random by construction in something like a Siena model, or a permuted version of your network using a QAP test or QAP test, depending on what you're calling, to ask whether or not, given this is the association I've observed, if I've compared that to a random network, would it be true? And the example I'm showing here is just whether or not we see that people who do business together are also people who are married to each other in 14th century Florence. And it turns out that, in fact, you can do what's called a permutation test, and you can see that 0.37 correlation would almost never show up by chance if you were to do it that way. Okay. So I'm going to stop there as sort of the first half of this notion of where we get to building models for the basic statistical questions of networks. And before I jump into what the logic behind ergon models, and just see if we have questions or comments up to this point. And I'm going to spill my soda all over myself. Does what I said so far make sense? Some head nods, completely ridiculous at some other point. Okay, Shannon, please.
Sorry to bother you again, but
No.
So Dr. Moody, when you were talking about those random graphs, and you're talking about, well, we're missing something, and sometimes it's degree, or sometimes is there such a thing, and when you're thinking about sociology, I know there is when you think about health and like those kinds of things like symptoms, but like mediators and moderators, and is there some way to sort of appreciate that statistically in the networks?
Yes, absolutely. That's a great question. So part of what you're trying to do in this, that's a good way to, thank you for that, because I should back up and point out how we got here. So what's going on in this case is I've explained a way of constructing your network by starting with a random graph and adding constraints such that randomization within that constraint gives you the network you observe. That's the logic behind network generation models in this framework. The other way to think about that is what causes a tie between two nodes. And so it's a classic causal model assumption, right? That if two people are the same, the probability that they have a tie between them, their similarity causes them to be tied, or more likely, their dissimilarity prevents them from being tied, right? And whenever you put it into that version of the framework, what you're really doing is saying, I've observed in a configuration of all these possible ties and non-ties, each of which are caused by something else going on in the network. And so anything that you can think of as a causal process can always have a mediating process. So for something like homophily, two nodes that are more like each other are more likely to be friends than two nodes that are not like each other. Then the general sort of causal mechanism we think is driving that is probably something like comfort or familiarity or trust, that I'm fearful of people who are different from me, so I'm unlikely to form a relationship. And so that means, so if that mechanism is true, if it's an anti-fear mechanism, then if I were to able to somehow control for my fear of some folks, that might explain why I have relationships with other folks net of our differences. So yes, any of the kind of moderation and mediation features that you could imagine in a standard dependent variable model can certainly happen here. The main difference is that instead of a single vector being your dependent variable, it's this n by n array that we call an adjacency matrix, and that whole adjacency matrix is your dependent variable. Does that make sense? Great.
Thank you.
You're also foreshadowing dimensional models. You have latent space models way
Those
at
are
the end of the.
exactly. Those are coming.
Yeah. So that's so Jim's thing is basically talking about what generates a tie, and you can kind of think of it as like a really fancy logistic regression for each of these ties. And he'll go into that in more detail. The other way to think about it is, okay, this network exists and I have dimensions like race or gender or things that organize the system, and I can think of those as latent variables. So I'm just pointing out that there's sort of at least two flavors about that question right in itself.
Right. Other questions?
I have a question about that slide you showed with all the different models and their progression, like Sienna and latent space. Like for me, who doesn't know well the difference between all those different approaches, is it obvious which one you use based on the data and the research question, or is there still a lot of disagreement, or how do we get our head around like which one's appropriate for this research question versus that?
Yeah, I think that the short answer is, well, boy, the short answer is probably no, but I think pragmatically, yes. So Sienna models are, that usually it's the case that your models, and I'll talk through sort of the which ones are best for what kinds of problems later, but yes, the answer is that, well, you could probably contort most models to answer most questions. Some models are much better at answering certain questions than others. And the big difference is whether or not your dependent variable is the network or an outcome from the network. So if what I'm trying to explain is why people are tied to each other, or how strongly they're tied to each other, you're valued. So if the dependent variable is a relationship question, then that takes you down this ergom branch and latent space model branch of this tree. So you go down over here. If instead what you're interested in is explaining why people are healthy or why people get a disease or what makes people happy, and you think one of the answers to this is who they're tied to and how those relationships are configured, then that leads you down the Siena model, a QAP network autocorrelation kind of model. And so the big division here in this final split is really between, am I trying to explain an outcome on the nodes, so what makes a node different from another node, or am I trying to explain an outcome on the edges, like why are two nodes tied to each other? And the one place where they get conflated, and you could sort of put them back together, is the Siena model. So what the Siena model does, it says that we're going to explain both simultaneously, but it comes with this big asterisk, only in the situations where the data are dynamic. So you have a temporal sequence that would allow you to disentangle those two. Does that help?
And it simulates a sequence. You don't necessarily have to have all the time.
Right.
It basically, it often comes with an assumption that the nodes are like really little agentic actors, where in some of the other questions, your nodes could be something else. Your nodes could be words, it could be whatever. And
Right.
these actors are acting across a time sequence that it simulates.
There's two questions in the chat that I want to bring attention to here. And if that's okay with the people who asked them, I'll just summarize it. But Dave Hunter was wondering if you could clarify your use of cause versus association.
Yeah, absolutely. Thanks, Dave. So the question, the answer to the question about cause versus association is a deep one, and I was using it in reference to a question about mediation and moderation. And so the concepts of mediation and moderation are only sensible in the setting with which you add some notion of cause. And so there, I really mean cause. Now, whether it's the case that your model actually captures cause, that the estimate on an urban model or a QAP or something is actually causal versus associational is a design question by and large, and a belief in your model specification question. And under a certain set of very strong assumptions, most of which are probably not met, then that would be the case, that you can do that. The Siena model is attempting to create a causal association, to disentangle some of these features. Again, it comes with a certain set of assumptions that I think you'd be hard pressed for the really hardcore causal modelers to believe. But I think that that is the underlying goal, is to at least narrow down the stream of associational constraints strong enough so that if there is a threat to the causal inference here, that threat is at least bounded. Is that a fair? Dave, feel free to unmute and tell me I'm crazy.
Not at all crazy, Jim. And I'm sorry, my smart-ass comment was the stat instructor in me. It actually, I didn't actually see where you're going to take that. That was a really interesting point that you made, though. And Joseph Quinn made essentially the same point in a private message. So thank you, Joseph.
Yeah, no, I think it really is the case, right? That and I think this is an important question, and it's one that those of you that saw my intro slides, I am, having spent 20 years in this business now, like sick to death of selection versus influence as the very first critique that people give. It's kind of like asking nature versus nurture, and I think oftentimes the causal modeling questions become that kind of reflexive gotcha, as opposed to saying, well, like, there's some cause, there's some noise, and the two are intermingled in a way that God only knows what the hell's going on. The problem is that's an honest answer, and reviewers don't want that. And so the pragmatic sort of careerist in us have to come down one side or the other, as opposed to the people who are just trying to understand the world around us as best we can. And I think that's unfortunate. I think the good news is that the sociobiological folks have managed to get past that to some degree and just admit that the world is conflated and we do the best we can. And when we have opportunities to identify strict, strong, powerful causal tests, we grab them, like natural experiments or field experiments or other kinds of things. Like, believe it, like as miserable as this last year has been for all of us, it has been a great interrupted time series. I mean, there's going to be so many wonderful natural experiments that have come out of this last year. That's going to be great for social science on that sort of base knowledge set, despite the fact that we made us all miserable. But on the other hand, when you've been given a data set that you have to play with, the best you can do often is to try to make sense of what's there, which is, and we'll get to this at the end here, but part of what I love about some of the work that's been done in this sort of spilled out of the causal inference framework has been to think really hard about bounds. And so it's often rarely the case that I can give you an exact estimate of the causal effect of homophily on tie formation, or sort of similarity on tie formation, which we would label homophily. But I can tell you how big a confounder would have to be to make that association go away. And so if the kind of threat to inference that you're worried about is an upstream confounder that I didn't include in the model, then at least I can bound what that might be. And those kinds of sensitivity analyses, I think, are often the pragmatic solution to these problems. Is that a fair rant? Somebody?
And then we had another question by Heifei too, but I think it's about, is there any restrictions regarding setting up ergms, like how many nodes and ties needed for adding additional variables? And we have about like 4 minutes to the break, and I think that's what you're going to be talking about after the break.
Exactly. I'm gonna ease us into basic ergm models from the P1 model next, and so I'll talk about that. The short answer is it's like anyone, it's a degree of freedom problem. So and the beauty of standard errors is that they account for your degrees of freedom. So so in principle, yes, you can, the limits are given by the data structures, but in practice there are some limits in terms of how long you're willing to wait for a result. Awesome. So let's go ahead and any other thoughts or comments on these big picture questions? Again, I encourage you to go out and find some of these histories. And like I said, Stan Washman has a nice history he just put out. And there's a lot of great work that's been coming out of the machine learning side of this that we're not even going to get into about prediction models versus explanation models. But for those that are interested in this baseline randomization stuff, I think there's a lot of really fun things coming in there. All right, since we're back on schedule then, let's take a couple minutes break. We got 8 minutes then, and we'll come back at 13:20 and start on this again.